Hello there, and welcome to the Sleepy at Night channel. Tonight, we drift into the hidden world of electricity, a force so familiar that we hardly notice it, yet so ancient and mysterious that it has shaped the universe since its earliest moments. Electricity is the quiet pulse inside every storm cloud, the shimmer behind every thought, and the delicate thread connecting matter, life, and light. It weaves through the cosmos, through the planet beneath your feet, and through the living architecture of your own body as you settle and imagine, tracing this invisible power from the heart of the thunderstorm to the depths of your mind, from the sparks of newborn stars to the soft glow of a lantern in the dark. Our journey will explore how electricity moves, transforms, and reveals the hidden workings of nature, carrying wonder in every direction it flows. If you enjoy these quiet journeys, I invite you to subscribe, or share a thought below. It helps others find their way here to one sleepy soul at a time. But for now, breathe, gently let your eyes grow heavy, and allow your mind to soften. Let's begin. Electricity is the silent architecture of every living cell inside every organism, from the smallest microbe to the most complex human being. Electricity provides an invisible framework that allows life to function with astonishing precision. Each cell maintains a delicate balance of charged particles across its membrane, creating tiny voltage differences that act like the language of biology. These charges determine when nutrients enter, when waste leaves, and when chemical reactions begin. Ion channels behave like microscopic gateways, opening and closing in response to subtle electrical cues, guiding the cell through every step of its existence. Even the simplest life forms rely on these currents to sense their surroundings, to move, and to adapt. Without this constant flow of charge, the instructions encoded in DNA would remain silent, because the machinery that reads and interprets those instructions depends on these electrical gradients. In this way, electricity forms the quiet structural backbone of life, a continuous whisper inside every living cell that shapes growth, healing, movement, and awareness. Lightning reveals the sky's most ancient form of electrical power. Long before humans learned how to store charge or send currents through copper wires, the planet displayed its own breathtaking demonstrations of electrical energy through lightning. These massive discharges form when storm clouds accumulate charge, often through countless collisions between ice particles that separate positive and negative regions within the cloud. When the electric field becomes strong enough, the atmosphere can no longer resist, and the charge leaps across the sky in a burst of light that reshapes the air itself. The flash heats the surrounding atmosphere to extraordinary temperatures in an instant, expanding it so violently that thunder becomes the audible signature of the event. Lightning even helps regenerate compounds in the atmosphere that are essential for long-term planetary balance. It can strike far from the storm that created it, branching unpredictably across the landscape. For countless generations of life, lightning has been both a force of fear and a spark of creation, offering a glimpse into the planet's natural electrical engine. Your body generates its own electrical messages every moment. Every sensation you feel and every movement you make begins as an electrical signal traveling through your nerves. These signals are created by shifts in the balance of ions surrounding nerve cells, which makes each cell capable of firing a rapid electrical impulse known as an action potential. When something touches your skin, tiny receptors convert that physical event into an electrical wave that travels with remarkable speed toward your spine and brain. The message remains purely electrical until it reaches the end of a nerve, where it is translated into chemical signals that cross the tiny space between cells and ignite a new electrical pulse on the other side. This relay continues endlessly, forming a living network that keeps you aware of your environment and allows you to react instantly to the world around you. Even when you sleep, your body constantly generates these signals, regulating breathing, heart rhythm, and countless internal processes. Without your awareness, the brain's thoughts form through cascading electrical storms. Every idea, memory, emotion, and decision exists because billions of neurons in your brain create intricate patterns of electrical activity. These patterns arise when Electrically charged ions move across neuronal membranes, allowing each cell to fire a rapid pulse that influences its neighbors. The brain contains countless branching connections, and each electrical spike travels along this network, like a spark moving across an impossibly dense forest of pathways. When groups of neurons fire rhythmically together, they form brain waves, large-scale electrical patterns that reveal your state of consciousness: calm, reflection, focused attention, dreaming, and deep sleep. Each display their own distinct waves. The most remarkable part is that the brain constantly reshapes these patterns as you learn and experience new things. Synapses strengthen or weaken based on electrical activity, allowing memory to form through repeated patterns. In this way, your entire inner world of thought and imagination emerges from continuous electrical storms that flash silently within your mind. Birds use Earth's natural electric signals to navigate vast distances. Many migratory birds possess the remarkable ability to sense faint electrical cues that help them navigate across continents and oceans. The surface of the planet carries a natural electric gradient created by the interaction between the ground and the outer atmosphere. Birds appear to detect changes in this field, adding it to their navigational toolkit that already includes magnetic sensing, sun position, and environmental landmarks. Experiments suggest that certain receptors near the beak respond to tiny shifts in electric potential, giving birds awareness of altitude, weather changes, and even approaching storms. This sensitivity becomes invaluable during long migrations when visibility may be poor and magnetic signals may fluctuate. Birds combine multiple natural cues to maintain stable flight paths, and electrical awareness provides a subtle yet reliable guide. This ability reveals that many animals can interpret forces in the world that humans rarely notice, making their long journeys not only feats of endurance but triumphs of sensory sophistication. Trees share electrical warnings through their root networks beneath forests. An intricate underground world allows trees to communicate using subtle electrical changes transmitted through root systems and shared soil networks. When a tree experiences stress, perhaps from drought or insect damage, its internal electrical potentials shift. These shifts can travel through the connected roots to neighboring trees, alerting the community to potential threats. Some research indicates that these signals adjust how much water surrounding trees absorb or how quickly they release certain defensive chemicals. The soil itself, rich with minerals and moisture, acts as a natural conductor that carries these electrical pulses through surprising distances. Fungal networks intertwined with the roots may amplify or distribute the signals further, creating a complex electrical ecosystem that links individuals into a cooperative whole. This underground communication helps forests respond collectively to changing conditions, revealing that trees are far from solitary organisms. Their ability to share information electrically gives them resilience and unity that sustain entire ecosystems. The aurora glows because solar electricity meets Earth's magnetic shield. High above the surface, charged particles from the sun travel along Earth's magnetic field lines and collide with atoms in the upper atmosphere. These particles arrive as part of a stream known as the solar wind, carrying electrical energy across vast distances of space. When they reach the magnetic poles, they spiral downward and energize atmospheric gases, causing them to emit shimmering light in shades of green, red, and violet. The process is both electrical and magnetic, a dance between the charged particles of the sun and the invisible shielding enveloping the planet. Variations in solar activity can intensify these displays, turning the sky into rippling curtains of luminosity that stretch across the horizon. The aurora becomes a visual map of the planet's electrical interaction with the cosmos, revealing forces normally hidden from human senses. Each glow is the imprint of a charged particle completing a journey from the sun to Earth's atmosphere. Volcanoes create their own lightning through electrified ash. During an explosive eruption, a towering cloud of ash, dust, and gas surges into the atmosphere. Inside this turbulent plume, countless particles collide with one another, transferring tiny amounts of charge. With each impact, lighter particles tend to acquire positive charge, while heavier ones accumulate negative charge, causing the entire plume to behave like a chaotic electrical generator. As the separation between these charges increases, powerful electric fields form, eventually producing spectacular lightning within the volcanic cloud. These flashes illuminate the ash column in rapid bursts, revealing swirling structures that would otherwise remain hidden in darkness. Volcanic lightning provides scientists with clues about eruption dynamics, since the electrical activity reflects the vigor and turbulence of the plume. It also demonstrates that nature can generate electricity in environments far removed from thunderstorms. The phenomenon shows that electrical forces emerge wherever energetic particles collide in great numbers, transforming volcanic eruptions into some of the most electrifying spectacles on the planet. The air around us holds an endless sea of electric charge. Even on a perfectly calm day, the atmosphere carries a subtle but ever-present collection of charged particles that drift through the air like an invisible ocean. This background charge forms because sunlight constantly interacts with molecules in the atmosphere, knocking electrons free and creating ions that wander in every direction. Dust, pollen, water droplets, and even microscopic fragments of organic material collect and redistribute these charges. As they move, the ground beneath you usually holds a net negative charge, while the air above carries a slight positive one, forming a gentle vertical electrical gradient that spans the entire sky. This gradient becomes stronger near storms and weaker in dry, still conditions, yet never disappears completely. Even indoors, traces of this atmospheric electricity move through the air, influenced by airflow, humidity, and the materials surrounding you. Although most people never sense it directly, this constant drift of charge subtly influences cloud formation, particle movement, and even how easily you accumulate static electricity. The atmosphere behaves like a planet-sized electrical environment, alive with tiny movements of charge that continue day and night. Electric fields stretch invisibly between every object. You can see every object carries some distribution of electric charge, even if it seems neutral to the touch. These charges create electric fields that extend outward into the surrounding space, shaping how particles interact long before they ever make contact. Although invisible, these fields govern whether dust clings to a surface, whether hair rises from static electricity, and even how molecules bind to one another. The strength and direction of a field depend on the type and arrangement of charge on an object, and fields from different sources combine or repel in complex ways. Electric fields guide electrons within circuits, influence how lightning starts, and help suspended particles settle or disperse in the atmosphere. Even in deep space, electric fields determine how plasma moves around stars and planets. The entire physical world is structured by these invisible gradients that operate silently yet constantly around every form of matter, even empty space has a restless electrical nature. What we call empty space is far from empty. At extremely small scales, the vacuum sees with fluctuations of electric and magnetic fields that appear and vanish too quickly for ordinary senses or instruments to detect. Directly, quantum theory describes this restlessness activity as a continuous exchange of virtual particles that flicker into existence and disappear almost instantly. These fluctuations exert subtle forces that can push objects together or apart, influence the behavior of atoms, and even modify how light travels through space in certain conditions, such as between two closely spaced metal plates. The vacuum behaves differently than in the open, demonstrating that it possesses measurable electrical properties. These effects show that space itself is not a passive backdrop, but a dynamic medium with its own hidden structure. Every beam of light, every charged particle, and every electromagnetic wave travels through this shimmering quantum landscape. The electrical nature of the vacuum shapes the universe quietly but profoundly, revealing that even the apparent nothingness is alive with unseen motion. Electric eels can sculpt their environment with pulses of power. Electric eels generate astonishingly strong electrical discharges using specialized organs made of modified muscle cells that behave like biological batteries. These cells stack in long series so that When they all fire together, they produce a powerful electrical pulse. Capable of stunning prey or deterring predators, the eel does more than simply shock other creatures. It sends out gentle probing pulses that reveal its surroundings, almost like an electrical form of echolocation. These smaller signals allow the eel to sense objects, track moving animals, and navigate murky water where vision fails. Recent research shows that the eel can even manipulate the behavior of prey by delivering rapid flickering pulses that force muscles to contract, involuntarily revealing hiding places. Entire hunting strategies depend on this dynamic use of electricity. The eel shapes the world around it, bending the behavior of other animals with bursts of charge that ripple through the water, making it one of nature's most extraordinary masters of electrical control. Some fish communicate using invisible electrical fields in regions where visibility is limited and sound travels unpredictably. Certain fish species rely on weak electrical signals as a primary means of communication. These fish possess organs that generate faint but steady electrical field around their bodies. When another fish approaches, its presence distorts the field, allowing both individuals to sense each other without physical contact. Many species can modulate the frequency or pattern of their electrical output, sending messages that convey identity, sex, social status, or territorial boundaries. These signals can be incredibly precise, enabling fish to distinguish between members of their own species and others within the same habitat. Some species even engage in electrical duets, adjusting their frequencies to avoid interference in the graceful negotiation that maintains clear communication. This silent language allows complex social interactions in environments where other senses are limited. The world these fish inhabit is filled with hidden electrical conversations that reveal an entirely different way to perceive and interact with the environment. Static electricity can lift tiny particles into floating clouds of dust. When objects rub against one another, electrons may shift from one surface to the other, creating areas of positive and negative charge. At small scales, these charges can become strong enough to move lightweight particles such as dust, ash, or pollen. Under the right conditions, these particles lift from the ground and hover as if gravity has loosened its grip. In deserts, this effect contributes to swirling dust storms, where grains are lofted by winds but further sustained by electrostatic attraction between charged particles on the surfaces of distant moons or asteroids where gravity is weak. Static charge can cause dust to levitate and drift above the ground in shimmering halos. Scientists believe that certain patterns seen on lunar soil arise partly from this phenomenon. Even indoors, tiny specks can cling to screens, fabrics, or plastic objects because static forces overcome their weight. Although these effects might seem small, they reveal the surprising strength of electrical interactions in shaping the motion of particles that fill our world. Some minerals generate electricity simply by being compressed. Certain crystals and minerals possess a property known as piezoelectricity, which allows them to produce an electrical charge when squeezed, stretched, or bent. This occurs because their internal atomic structure is arranged in a way that lacks perfect symmetry. When pressure is applied, the balance of charge inside the crystal shifts, creating an electrical potential that can be detected on the surface. Quartz is one of the best known examples, but many other minerals and engineered materials share this ability. This property forms the basis of numerous technologies. Small sensors measure pressure changes by converting mechanical stress into electrical signals. Lighters use sudden compression to create sparks that ignite fuel. Even the tiny time-keeping crystal inside many watches relies on this effect to maintain a steady vibration pattern in the natural world. Piezoelectric minerals embedded in rocks may generate faint electrical signals during earthquakes or landslides, offering clues about geological stress. This remarkable coupling between pressure and electricity demonstrates how deeply intertwined mechanical and electrical forces can be. Crystals can convert motion into electrical charge beyond simple compression. Certain crystals transform many forms of mechanical motion into electrical energy when twisted, tapped, or flex their internal structure shifts in a way that separates charge and creates a measurable voltage. This ability has inspired devices that harvest energy from everyday activities, floors embedded with piezoelectric materials can capture the pressure of footsteps and convert it into small amounts of electricity. Sensors placed on bridges or buildings can translate tiny vibrations into continuous signals that monitor structural health. Even musical instruments can incorporate these materials to transform sound vibrations into electrical output. The phenomenon operates at the atomic level, where asymmetric arrangements of charged ions allow forces to redistribute electrons whenever the crystal moves. Engineers continue to search for new materials that enhance this effect, hoping to build systems that capture ambient vibrations from traffic, machinery, or ocean waves. Each of these applications relies on the simple but powerful principle that motion can be translated directly into electrical charge. Earth's surface acts like a massive electrical reservoir. The planet beneath your feet holds a vast store of negative charge, forming a natural electrical reservoir that interacts continuously with the atmosphere. Above, this charge distribution exists because solar radiation, cosmic particles, and weather processes constantly strip electrons from air molecules. Many of these electrons eventually return to the ground, maintaining a long-term balance. The surface behaves like a stable reference point for electrical potential, anchoring the global circuit that flows between the ground and the upper atmosphere. When lightning strikes, it briefly reconnects regions of separated charge, transferring immense energy back into the earth. The soil and rock also influence electrical flow, since moisture content, mineral composition, and temperature all affect conductivity. Some animals, such as burrowing insects or subterranean mammals, may even sense electrical cues in the soil as part of their navigation. This planetary reservoir allows countless electrical processes to occur safely and continuously, supporting both natural phenomena and the functioning of human technology. The planet is constantly wrapped in a global electric circuit. From the surface to the upper atmosphere, Earth maintains a continuous circulating flow of electrical energy. Thunderstorms generate strong upward currents that carry positive charge into the ionosphere, a region high above the clouds. At the same time, fair weather regions allow a slow downward flow of charge from the ionosphere back to the ground. Together, these currents create a planet-spanning loop known as the global electric circuit. Even when skies appear calm, this system remains active with gentle electric fields bridging the atmosphere and surface. Lightning, though dramatic, represents only one part of this circuit. Countless small-scale discharges, turbulent air flows, and ion movements contribute to the larger pattern. Researchers have discovered that variations in the global circuit may reflect changes in climate, volcanic activity, or solar conditions, making it an important indicator of planetary dynamics. This enormous electrical loop surrounds every living being, weaving the atmosphere and ground into a unified system that operates continuously. The ionosphere echoes with electrical waves that travel the entire world. High above the surface, the ionosphere forms a charged layer where ultraviolet light, an energetic particle from space, knock electrons loose from atoms. This region behaves like a natural electrical conductor, allowing low-frequency waves to travel extraordinary distances without weakening. These electromagnetic waves can reflect between the ionosphere and the ground, bouncing across oceans and continents in patterns that resemble echoes in a vast atmospheric chamber. This property enables long-distance radio communication, allowing signals to travel beyond the horizon. The ionosphere also responds to solar storms, which can temporarily change its density and disrupt wave propagation, creating beautiful but unpredictable variations in global electrical behavior. Animals, such as certain migratory species, may unconsciously sense these changes. The ionosphere stands as a dynamic electrical membrane surrounding the planet, a constantly shifting realm that carries waves capable of circling Earth again and again. Solar wind shapes Earth's electrical environment. Every day, a continuous stream of charged particles flows outward from the sun, bathing the solar system in a river of plasma. When this solar wind reaches Earth, it interacts with the magnetic field and atmosphere, influencing the planet's electrical balance. Strong gusts of solar wind compress the magnetosphere, altering how charged particles flow along magnetic lines, and sometimes intensifying auroral activity. Even during calm periods, the wind transports electric charge that gradually accumulates in the upper atmosphere. These subtle changes can affect radio communication satellite behavior and the structure of the ionosphere itself. At times, the solar wind carries embedded magnetic structures that reconnect with Earth's magnetic field, injecting additional energy into the system. The entire planet responds to these interactions, from shifts in atmospheric conductivity to electrical currents that circle the polar regions. The solar wind is a reminder that Earth's electrical environment is never isolated but constantly shaped by the dynamic activity of the sun. Thunderstorms pump gigantic currents into the upper atmosphere. Inside a towering thunderstorm, countless collisions between ice water droplets and rising air currents separate electrical charge into distinct regions. This process creates strong electric fields that drive lightning, but not all the current remains within the cloud. A portion flows upward toward the ionosphere, contributing to the global electric circuit. Upward, lightning, blue jets, and other high-altitude discharges propel charge far above the storm tops, forming spectacular electrical structures that stretch into thin air. These currents influence atmospheric conductivity and help maintain the planet-wide balance between ground and sky. Thunderstorms act as natural generators, constantly replenishing the electric potential of the upper atmosphere. Without them, Earth's electrical environment would gradually diminish. Their role extends beyond weather, as they also affect radio propagation, atmospheric chemistry, and the distribution of charged particles across the planet. Each storm becomes a dynamic engine that pumps electrical energy upward. With astonishing power, atoms hold their structure through purely electrical attraction. The stability of matter arises from the delicate balance between negatively charged electrons and positively charged protons. Electrons orbit the nucleus not because they follow tiny planetary paths, but because their electrical attraction binds them into specific energy levels. These levels emerge from the wave-like nature of electrons, which spread around the nucleus in patterns defined by their motion and charge. Without this electrical pull, matter would disperse into a shapeless cloud of particles. The arrangements of electrons determine how atoms bond, how molecules form, and how materials behave. Whether an object is brittle, flexible, metallic, transparent, or magnetic depends on how electrical forces constrain its electrons. Even the colors we perceive arise from these energy structures, since atoms absorb and emit specific wavelengths of light based on electron transitions. The familiar solidity of the world is a direct result of electrical attraction at the atomic scale, creating order from what would otherwise be chaos. Electricity is the force that allows matter to exist in stable form. Every physical object remains intact because electrical forces hold its particles together with extraordinary strength. Protons and electrons attract, electrons repel one another, and these interactions define the shape and structure of all matter. When you press your hand against a solid surface, you never actually touch it at the atomic level. Instead, the electrical repulsion between the electrons in your hand and those in the surface prevents the particles from overlapping. This repulsion creates the sensation of solidity. The behavior of metals, liquids, crystals, and gases all arises from the arrangement of electrons that electrical forces maintain. Even chemical reactions depend on how electrical attractions shift between atoms. When bonds break or form without electricity, atoms could not maintain stable boundaries. Molecules could not hold their shapes. Life could not assemble its complex structures. The stability of matter, from mountains to microorganisms, is an exquisite expression of electrical forces working in perfect balance. Electrons move in ways that break our ordinary sense of reality. Electrons do not behave like tiny balls traveling along predictable paths. Instead, they move according to the rules of quantum mechanics, which allow them to act like waves, particles, or something in between, depending on the situation. Inside atoms, electrons occupy allowed regions of space rather than fixed orbits spreading out in clouds of probability that define where they are likely to be found in materials electrons can flow freely, become localized, or form collective patterns that behave like new types of particles. They can pass through barriers that classical physics says should stop them, adjust their state instantly in response to distant changes, and interfere with themselves in ways that defy intuition. Their behavior forms the basis of modern electronics chemistry and even biological processes. Understanding electrons requires letting go of familiar ideas about motion and position and embracing a world where probability and wave-like behavior dominate. Electricity can flow without resistance in supercooled materials. In normal conductors, electrons move through a material while constantly colliding with atoms, which convert some electrical energy into heat. When certain materials are cooled to extremely low temperatures, they undergo a remarkable transformation in which electrical resistance drops to zero. In this superconducting state, electrons pair up in a coordinated dance that allows them to glide through the material without scattering. Currents in a superconducting loop can flow indefinitely without losing energy. This property allows for incredibly strong electromagnets, efficient power transmission, and sensitive scientific instruments. The transition to superconductivity also alters magnetic behavior, expelling magnetic fields from the material and creating striking effects such as floating magnets. Although scientists continue to search for materials that exhibit this phenomenon at higher temperatures, the discovery of superconductivity remains one of the most surprising revelations in physics. It demonstrates that electrical behavior can shift dramatically when matter approaches its quantum limits. Superconductors can levitate objects with their perfect currents. When a material becomes superconducting, it not only carries current without resistance, but also pushes magnetic fields out of its interior. This effect, known as magnetic flux exclusion, allows a magnet placed near a superconductor to be locked into position above or beside it in a stable floating state. The superconductor creates circulating currents on its surface that oppose the magnet's field holding it in place. Without physical contact, this levitation is incredibly stable, resisting tilting, sliding, or rotation. Engineers imagine using this effect for frictionless transportation, precision bearings, or ultra-stable platforms. For scientific instruments, the phenomenon reveals the astonishing power of coordinated electron behavior, since the currents that enable levitation flow without energy loss. Some materials remember past electric fields in mysterious ways. Certain substances exhibit a property known as ferroelectricity, in which their internal electric polarization can switch direction in response to an external field and then remain in that state even after the field is removed. This behavior acts like a memory of past electrical conditions inside these materials. Small regions, known as domains, align their dipoles in a particular orientation, creating stable patterns that encode information. These patterns can endure for long periods, making ferroelectric materials useful for memory storage, sensors, and precise control devices. The switching process involves tiny shifts in atomic positions that collectively produce microscopic changes in electrical properties. In some cases, temperature, pressure, or mechanical stress can influence how these domains form and reorganize. Researchers study ferroelectricity not only for practical applications, but also because it reveals deep connections between electrical behavior and atomic structure, the ability of a material to retain an imprint of past electric fields highlights the rich and surprising ways that electricity interacts with matter. Electricity can travel through certain materials as waves of vibration. In some solids, electrical interactions couple tightly with mechanical vibrations, forming a hybrid wave known as a phonon polariton. These waves allow energy to travel through a material not only as moving charge, but also as oscillations in the atomic lattice. This coupling creates new possibilities for controlling heat, light, and Electrical flow at microscopic scales. Materials that support these waves can confine energy into spaces much smaller than the wavelength of light, enabling miniature sensors and optical devices. The wave-like propagation also influences how materials emit or absorb infrared radiation, making them important for thermal imaging and energy harvesting technologies. In nature, similar coupling effects help regulate how heat spreads through minerals or biological tissues. The idea that electricity can move as a vibration rather than a simple flow of electrons expands our understanding of how energy travels through condensed matter. Quantum tunneling allows electric charge to slip through barriers in the quantum world. Particles, such as electrons, can sometimes appear on the other side of a barrier. They seemingly should not be able to cross. This process, known as quantum tunneling, occurs because electrons behave partly like waves and can extend into regions that classical physics would forbid. If the barrier is thin enough, part of the wave can continue beyond it, allowing the electron to emerge as if it had passed directly through. Tunneling plays a crucial role in many technologies, including scanning microscopes that map surfaces by detecting tunneling currents and components that regulate electron flow in advanced circuits. It also influences natural processes inside stars. Tunneling enables nuclear fusion by allowing charged particles to overcome electrical repulsion. In biology, certain reactions depend on tunneling to move protons or electrons between molecules. This phenomenon demonstrates how quantum mechanics shapes both the smallest scales of technology and the largest scales of the universe. Electron spin creates tiny magnetic fields that shape all technology. Electrons possess an intrinsic angular momentum known as spin, which gives rise to a magnetic moment. Even when the electron is not moving through space, this tiny magnetic property influences how atoms form bonds and how materials exhibit magnetism. In ferromagnetic materials, the spins of many electrons align, creating strong magnetic fields that power motors, data storage devices, and countless tools. Electron spin also lies at the heart of innovative technologies such as spintronics, which uses spin states rather than charge flow to store and process information. These spin-based devices promise faster operation with lower energy consumption. On a deeper level, the alignment and interaction of electron spins determine the magnetic structure of planets, the behavior of stellar remnants, and even the properties of exotic materials like quantum magnets. The simple fact that electrons possess spin allows for a universe shaped by magnetic interactions, both familiar and extraordinary. The flow of electrons can become organized like a perfect dance. When electrons move through certain materials, they do not always travel randomly. As individuals colliding with atoms under the right conditions, their motion can become coordinated, forming collective waves that move with remarkable grace and precision. This organized flow appears in materials where electrons interact strongly with one another, creating patterns that resemble synchronized motion across a vast ensemble. The behavior can influence electrical resistance, heat transport, and even optical properties. In metals near absolute zero, electrons can adopt unusually smooth flow patterns that resemble fluid movement. In some exotic materials, they arrange themselves into repeating structures that alter conductivity in complex ways. Scientists continue to discover new examples of these coordinated dances, from swirling patterns that shape magnetic behavior to oscillations that influence superconductivity. The study of these flowing electron states reveals that electricity can move with elegance far beyond simple current. It behaves as a collective system in which countless particles merge into unified motion. Metals carry electricity because their electrons roam almost freely inside a metal. Many electrons are not tied to individual atoms. Instead, they drift through the material in a shared sea that spans the entire structure. This freedom arises because metal atoms arrange themselves in a repeating lattice, allowing their outer electrons to overlap and form a communal sea of charge. When an electric field is applied, these free electrons respond instantly by shifting through the lattice, creating the current that powers devices and lights. The efficiency of this movement depends on temperature, crystal structure, and impurities within the metal. As the material cools, the atomic lattice vibrates, less allowing electrons to flow more smoothly. This is why some metals become significantly better conductors at lower temperatures. The free movement of electrons also gives metals their characteristic shine, since incoming light interacts with the electron C and reflects outward. This combination of optical and electrical properties makes metals essential to modern technology and ancient craftsmanship alike. Insulators protect us by holding their electrons firmly in place. In insulating materials, electrons are bound tightly to their atoms, making it extremely difficult for electrical charge to move through them. This stability arises from strong chemical bonds that keep electrons locked in place, preventing the formation of free carriers that could create a current. Materials such as rubber, glass, and certain plastic rely on this behavior to shield people and equipment from unwanted electrical flow. When voltage is applied across an insulator, the electrons resist displacement, preserving safety and maintaining separation between conductive components. The insulating properties depend on molecular structure, internal defects, and environmental factors, such as humidity. In nature, many organisms depend on insulating layers to protect sensitive tissues from electrical fluctuations in the environment. Even the atmosphere itself acts as a partial insulator until electric fields grow strong enough to produce lightning. The ability of insulators to confine electrons makes them indispensable for controlling the powerful forces associated with electricity. Semiconductors behave like controlled gateways for electricity. Semiconductors occupy a unique middle ground between conductors and insulators. Their electrons are not entirely free, yet they can move when encouraged by light, heat, or an applied voltage. This tunable behavior arises from the carefully arranged structure of atoms within the semiconductor and the presence of energy bands that determine how electrons can move. By introducing small amounts of other elements into the material, engineers can adjust how easily electrons or holes flow, creating regions with specific electrical properties. These regions work together to form diodes, transistors, and countless components that underpin modern electronics. The ability to control electron flow with such precision allows semiconductors to amplify signals, switch currents, and process information. Their behavior changes with temperature and illumination, making them ideal for sensors and photovoltaic devices. Semiconductors provide the foundation for computing, communication, and energy technologies, transforming controlled electron movement into an entire digital world. Transistors use tiny electrical decisions to build entire worlds of logic. A transistor operates by allowing or blocking the flow of electrons, depending on the small input signal. This simple action becomes incredibly powerful when billions of transistors are arranged into circuits that perform logical operations. Each transistor acts like a switch that controls where the current flows in a particular pathway, enabling computing systems to carry out mathematical processes, store data, and execute complex instructions. When these switches act together, they can represent information, compare values, or direct signals along branching routes. The speed at which transistors change state determines how quickly a computer can operate, and engineers continually refine their design to reduce energy use and increase efficiency. Although each transistor is tiny, their collective behavior forms the backbone of modern digital life. Everything from navigation systems to medical devices depends on these electrical decisions made at microscopic scales. The transistor stands as one of humanity's most transformative inventions, translating the motion of electrons into logic, communication, and creativity. Computer memory stores information as patterns of electric charge. Many types of computer memory rely on the presence or absence of charge to represent information. In some memory systems, tiny capacitors hold a small amount of electrical energy that indicates whether a bit is interpreted as one state or another. Other technologies trap electrons within insulating layers, allowing data to persist even without a power source. The stability of these stored charges depends on material structure, temperature, and precise engineering. Reading the information involves detecting tiny differences in voltage or current. Writing data requires altering the distribution of electrons within microscopic cells. As technology advances, Memory components shrink to astonishingly small sizes, allowing vast amounts of information to be packed into compact devices. This reliance on electric charge shows that even the most abstract digital concepts ultimately rest on physical processes. Every photograph, message, or program in modern computing exists because electrons can be arranged into stable, retrievable patterns. Every digital image you see is formed by rivers of electrical signals before a picture appears on a screen. It begins as an intricate flow of electrical information passing through circuits, processes, and memory. Each pixel corresponds to small electrical values that define its color and brightness. These signals travel along pathways shaped by transistors, amplifiers, and timing systems that synchronize the movement of electrons with remarkable precision. In cameras, light is converted into electrical charge by sensors that respond to incoming photons. This charge is then interpreted and stored as patterns that represent the scene. When displayed, the electrical instructions for each pixel are sent to the screen, where they direct tiny elements to produce the correct color. The rapid coordination between millions of electrical signals allows images to update in smooth sequences, forming videos and interactive displays. Although digital pictures seem effortless, they rely on continuous currents of electricity flowing through carefully designed systems that translate information into visible form. Electricity allows lasers to produce perfectly ordered light. A laser creates an exceptionally pure beam of light by stimulating atoms or molecules to emit photons that share the same direction, frequency, and phase. Electricity provides the energy needed to excite these atoms into higher energy states. When one of them releases a photon, it triggers neighboring atoms to emit identical photons, creating a cascading process known as stimulated emission. The result is a concentrated stream of light that could travel great distances without spreading significantly. Electrical control allows engineers to fine-tune the laser's properties, adjusting brightness, color, and pulse duration for applications ranging from scientific research to medicine. Lasers can cut metal with high precision, read data from storage devices, or measure distances with extraordinary accuracy. All of these abilities depend on the electrical energy that drives the initial excitation, proving that electricity lies at the heart of one of the most precise tools ever created. Plasma displays work by exciting glowing electrified gas in a plasma display. Each pixel contains a tiny cell filled with gas that becomes ionized when electrical voltage is applied. The ionized gas emits ultraviolet light, which then strikes a layer of phosphor coating inside the cell. This phosphor converts the invisible ultraviolet light into visible colors by controlling the electrical pulses delivered to each cell. The screen produces a wide range of hues and brightness levels. The rapid switching ability of plasma cells allows for smooth motion and vivid contrast. Although newer technologies have become more common, plasma displays remain an important demonstration of how electricity can shape light through the behavior of ionized gas. The glowing plasma within each pixel behaves like a miniature lamp that brightens and dims based on precise electrical control, revealing how complex images can emerge from the behavior of electrified matter. At microscopic scales, electric motors turn invisible forces into physical motion. An electric motor converts electrical energy into mechanical motion by using the interaction between magnetic fields and moving current. When electricity flows through coils of wire inside the motor, it generates magnetic forces that push and pull on a rotor. As the rotor spins, these forces continuously shift to maintain rotation. The smooth operation of a motor depends on carefully designed components that guide the magnetic interactions and minimize energy loss. Different motor types use various methods to switch current direction, control speed, or enhance torque, but all rely on the fundamental relationship between electricity and magnetism. Electric motors power countless devices, from fans and household appliances to industrial machinery and transportation systems. Their ability to transform invisible electrical forces into motion makes them one of the most important technologies in the modern world, demonstrating how profoundly electricity shapes our physical power environment. Human motion can be turned into wearable electrical energy The human body produces continuous movement through walking, stretching, bending, and natural shifts in posture. Mechanical motion at these scales can be captured by flexible materials that convert pressure or bending into electrical charge. Some of these materials create charge when stretched, while others generate it from repeated compression. When incorporated into wearable devices, these materials harvest energy from ordinary actions without requiring conscious effort from the wearer. The electricity produced can power sensors that track movement, measure environmental conditions, or monitor health indicators. The effectiveness of these systems depends on material flexibility, durability, and the ability to collect charge without restricting. Motion engineers explore a variety of structures, including woven films, layered polymers, and tiny embedded generators that respond to motion at specific points of the body. This approach allows energy to be gathered continuously from activities that people already perform. It shows that the human body is not only a source of movement, but also a potential contributor to small-scale power systems that operate quietly and independently. Electric textiles may one day power clothing from body movement. Advances in material science have made it possible to integrate conductive fibers, flexible circuits, and charge-generating structures directly into fabrics. These textiles can react to bending, stretching, or rubbing by producing small but measurable electrical signals. Unlike rigid devices, they move seamlessly with the body, preserving comfort while adding new functions to everyday clothing. Patterns of conductive threads can distribute the generated charge across different regions of the textile, allowing the energy to be collected and stored for later use. The choice of fiber weave and coating affects how efficiently the material responds to motion. Some designs combine conductive pathways with micro-storage elements, creating fabrics that both generate and hold energy. Potential applications include health monitoring systems, navigation aids, and emergency signaling tools that operate without external power. The development of electric textiles suggests that clothing could evolve from a passive layer of protection into an active energy harvesting surface that interacts directly with the wearer's movements. Wireless charging sends energy through invisible fields of power. Electrical energy can be transferred without physical contact by creating an oscillating magnetic field that induces current in a nearby device. This process depends on two coils tuned so that energy passes efficiently from one to the other. When they're placed close together, the transmitting coil generates a varying magnetic environment, and the receiving coil responds by guiding electrons into motion. The effectiveness of this method depends on coil alignment, distance, and the materials surrounding the system. Engineers refine coil geometry and frequency to improve power transfer while reducing energy loss. Wireless charging allows devices to replenish their stored energy without exposed connectors or direct wiring, providing convenience and reducing wear on components. The technique can be extended to larger systems where embedded coils in floors, vehicles, or furniture provide power to compatible devices. This approach demonstrates that magnetic fields can act as intermediaries in the transfer of electrical energy, creating new possibilities for how devices connect and interact. Induction cooking heats metal without flames through electric fields. A cooking surface that uses induction relies on alternating magnetic fields to generate heat directly inside compatible cookware. When a field passes through the metal, it induces circulating currents that encounter resistance within the material. This internal resistance produces heat, warming the pot or pan without heating the surrounding air or the cooking surface itself to the same degree. The process offers rapid temperature changes because the energy is delivered straight into the cookware rather than through an intermediate heating element. The efficiency of the system depends on the magnetic properties of the metal, the thickness of the cookware, and the strength of the field. Induction cooking provides precise control and reduces energy waste, as the heat is concentrated where is needed. It also enhances safety because the surface cools quickly once the cookware is removed. This method illustrates the close connection between magnetic fields and electrical currents and shows how electromagnetic principles can reshape everyday tools. Magnetic levitation trains glide using electrically controlled forces. Some transportation systems rely on electromagnetic interactions to lift and propel vehicles without physical Contact between wheels and tracks. These systems use controlled magnetic fields generated by coils within the train and along the guideway. When currents flow through the coils, they create forces that counteract gravity and push the vehicle forward. The absence of friction between surfaces allows the train to move smoothly with minimal mechanical, where engineers monitor field strength alignment and timing to maintain stability and ensure that the train remains centered on the track. The precision required for this system is significant, yet the result is a mode of travel that blends speed with near-silent operation. The ability to lift and guide large structures using only electromagnetic forces demonstrates the power of coordinated electrical control. It reveals how magnetic principles can be scaled from laboratory devices to transportation systems capable of carrying passengers across long distances. Electric vehicles convert stored charge into silent propulsion vehicles powered by electrical energy, rely on stored charge within battery systems, and convert this charge into motion using electric motors. When current flows through the motor's coils, magnetic forces develop that turn the rotor and drive the wheels. The absence of combustion allows the system to operate quietly and with fewer mechanical vibrations. The performance of an electric vehicle depends on battery chemistry, motor design, power management systems, and the efficiency with which energy is recovered during braking. Engineers work to improve how quickly energy can be stored, how far a vehicle can travel on a single charge, and how effectively heat is managed during operation. The driving experience feels smooth because the motor provides consistent torque across a wide range of speeds. Electric vehicles demonstrate how advances in electrical storage and motor technology can reshape transportation, reducing reliance on combustion and highlighting the versatility of electrically driven motion. Batteries store energy through reversible chemical electricity. A battery holds energy by arranging materials so that chemical reactions release electrons in a controlled manner. When the battery powers a device, the internal chemistry shifts and electrons travel through an external circuit before returning to the opposite side of the cell. During charging, the applied current reverses the chemical changes and restores the original arrangement. The materials inside a battery determine how much energy it can store, how quickly it can release that energy, and how many times it can complete the cycle. Engineers explore new combinations of metals, electrolytes, and separators to improve performance and durability. Temperature, discharge rate, and chemical stability all influence how effectively a battery operates. This reversible relationship between chemistry and electricity allows portable devices, vehicles, and backup systems to function without direct connection to a power grid. The battery serves as a bridge between chemical energy and electrical output, enabling countless technologies to operate independently. Flow batteries hold electrical energy in liquid form. A flow battery stores energy using liquid electrolytes that circulate through external tanks and across a central cell, where electrochemical reactions occur. Unlike solid-state batteries, the energy capacity of a flow system depends primarily on the size of the storage tanks, rather than the internal cell itself. During discharge, the flowing liquids release electrons that move through an external circuit, and during charging, the process reverses to restore the chemical composition of the electrolytes. This design allows for long cycle life because the reactive materials remain in solution and experience less structural stress. Operators can increase storage capacity simply by expanding the tanks, making flow batteries attractive for large-scale energy storage, such as stabilizing electrical grids. The efficiency of the system depends on pump performance, membrane selectivity, and the chemical properties of the electrolytes. Flow-based storage demonstrates a flexible way to manage large quantities of electrical energy using circulating liquids rather than solid materials. Ultracapacitors release electricity in bursts of incredible speed. An ultracapacitor stores electrical energy by accumulating charge along the surfaces of specially designed electrodes separated by a thin insulating layer. When energy is needed, the stored charge can be released almost instantly because it does not rely on slow chemical reactions the rapid discharge makes these devices useful for applications requiring sudden bursts of power, such as stabilizing Voltage supporting quick acceleration or maintaining performance during short interruptions in supply. Their ability to charge quickly also makes them well suited for repeated cycling. The amount of energy an ultracapacitor can store depends on electrode surface area, electrolyte composition, and the distance between charge layers. Although they cannot store as much energy as batteries of similar size, their speed and durability allow them to complement other storage technologies. Ultracapacitors illustrate how electrical energy can be managed through physical charge separation rather than chemical transformation, creating systems optimized for rapid response. Lightning rods guide electric storms safely into the ground. A lightning rod provides a controlled pathway for electrical discharge during a storm by presenting an elevated point that attracts the developing strike. The rod connects to a low-resistance conductor that leads into the ground, allowing the charge to dissipate safely rather than traveling through buildings or other structures. The effectiveness of the system depends on proper placement, grounding depth, and the conductivity of the surrounding soil. When approaching storm builds strong electric fields, the rod becomes a preferred channel for the impending discharge. The current then flows through the designated conductor and spreads harmlessly into the earth. This method prevents damage to structures and reduces fire risk by ensuring that the electrical event follows a predictable route. Lightning protection systems demonstrate how understanding natural electrical behavior can prevent harm and allow powerful atmospheric forces to be managed with simple, well-designed components. Generators transform spinning motion into streams of electrons. Electrical current can arise from something as simple as a turning shaft moving within a magnetic environment. As the internal components rotate, the magnetic landscape inside the device changes, and the electrons in the surrounding metal respond by drifting into an organized path. The behavior depends on the arrangement of coils, the strength of the magnetic field, and the steadiness of the rotation. Water pressure, moving air, expanding vapor, or mechanical engines can all supply the initial motion that keeps the system turning inside the generator. Nothing is created or destroyed. Instead, existing electrons are encouraged to move in a coordinated stream that emerges as usable electrical power. This conversion from mechanical motion to electrical flow supports nearly every major energy network in the world. It highlights the remarkable fact that electrons respond reliably to a shifting magnetic environment, forming a stable current from something as subtle as a rotating coil. The process demonstrates how mechanical forces can become the basis of electrical systems that reach across entire continents. Turbines use nature's movement to create vast electrical currents. Moving fluids contain tremendous kinetic energy, and a turbine is designed to capture that energy by guiding the flow along carefully shaped blades. As the fluid passes through, its momentum causes the blades to sweep in a circular path that turns a central shaft. The rotation travels into a generator that converts the mechanical motion into an electrical stream. The behavior of the entire system depends on the geometry of the blades, the steadiness of the fluid, and the alignment of the components that carry the rotation. Steam rising through a power plant, water moving down a channel, or air rushing across open land can all serve as the force that sets the turbine in motion. Engineers evaluate turbulence, blade angle, and structural stability to ensure the motion remains smooth and predictable. This arrangement links natural movement directly to electrical production, turning the planet's existing energy flows into a stable and renewable supply of current. It showcases how fluid motion, long present in the world, can become a foundation for large-scale electrical systems. Hydroelectric dams convert falling water into powerful electricity. Stored water contains potential energy simply because it sits above a lower surface. When released from a reservoir, the water accelerates through narrow passages with increasing force as gravity pulls it downward. This motion strikes the blades of a large turbine, causing a steady rotation that then drives a generator. The reliability of this arrangement comes from the stability of the water cycle itself. Rainfall, snow melt, and seasonal patterns refill the reservoir, allowing continuous operation. Engineers monitor water pressure, flow rate, and structural integrity to ensure consistent performance. The energy extracted from the falling water depends on the difference in height, the design of the channels, and the responsiveness of the turbine. Because the process produces no combustion, it provides a clean and long-lasting source of power. Hydroelectric systems illustrate how gravitational potential, a simple feature of the natural world, can be transformed into electrical energy that supports cities, industries, and remote communities alike. Wind farms capture invisible air currents for electric power. Moving air carries kinetic energy that can be collected when aerodynamic blades shape the flow into rotation. As the air passes, each blade differences in pressure form across the surface, producing lift that turns the rotor. The turning motion travels down a shaft and into a generator, where magnetic fields guide electrons into an organized current. The ability to extract power depends on blade length, air density, atmospheric stability, and the arrangement of machines across the landscape. Taller towers reach steadier currents, while offshore placements benefit from the smoother motion of air moving over open water. The rotation remains gentle yet persistent, allowing the system to produce large amounts of electricity over long periods. What makes this approach remarkable is how it links atmospheric motion, something that flows freely across the planet, to electrical networks that support modern life. Carefully engineered blades transform invisible air currents into steady and renewable electrical output. Solar cells use light to liberate electrons directly. Light arriving from the sun carries energy in the form of photons, and a photovoltaic device uses that energy to free electrons within a semiconductor. When photons strike the material, they can excite electrons enough to break them away from their usual positions. The internal structure of the device creates an electric field that guides the newly freed electrons towards specific pathways, forming a direct current. The performance depends on how efficiently the material absorbs light, how easily the electrons can move once excited, and how well the device manages the separation of charges. Different semiconductor compositions allow engineers to tune the response to various wavelengths of light. Layers of conductive metals, transparent coatings, and protective films all contribute to the overall function. The result is a technology that converts sunlight into electrical energy without moving parts. It demonstrates how light itself can serve as a direct source of charge motion when paired with a precisely engineered material. Geothermal plants tap Earth's heat to drive electric generation. Heat rising from within the planet can be used to boil water or heat specialized working fluids, producing vapor that expands with considerable force. This expanding vapor moves through turbines designed to extract rotational energy from the flow. The rotation then enters a generator, where electrons begin to move under the influence of shifting magnetic fields. Geological formations rich in porous rock and naturally heated underground reservoirs make this process possible. In certain regions, engineers drill into these formations to access the thermal energy and circulate fluid through them. The reliability of geothermal systems stems from the steady heat emerging from deep within the earth. Because the temperature difference remains consistent, the plant can operate with remarkable continuity. This arrangement transforms natural geological warmth into electrical current, showing how heat that has been inside the planet for ages can support modern energy systems. Tidal energy pulls power from the rhythms of the moon. Ocean water rises and falls in predictable cycles, driven by the gravitational interaction between the Earth and its lunar companion. These rhythmic movements carry kinetic energy that can be harvested when flowing water passes through underwater turbines or channels designed to accelerate the current as the water moves through the system. It turns blades that rotate a shaft connected to a generator. The reliability of this resource comes from the stability of the orbital relationship that governs the tides. Coastal regions with narrow inlets or strong tidal currents provide especially effective locations for energy extraction. Tidal systems must be engineered to withstand corrosive salt water, shifting sediment, and powerful waves. Yet when designed, they offer a clean and highly predictable source of electrical energy. This method of generation connects celestial mechanics, ocean motion, and electrical production in a way that highlights the ongoing influence of the moon on life and technology. Some microbes create electricity as part of their metabolism. Certain microorganisms have evolved the ability to transfer electrons outside their own cells as they break down nutrients. This unusual capability allows them to interact directly with minerals or other surfaces in their environment as electrons move outward. They create measurable electrical currents that scientists can detect and study. These microbes live in diverse settings, including riverbeds, wetlands, and soils rich in organic material. Their metabolic pathways rely on specialized proteins that shuffle electrons across cell membranes and onto external structures. The strength of the current depends on nutrient availability, temperature, and the composition of the surrounding medium. Researchers are exploring ways to harness these natural electrical processes for sensors, environmental remediation, and miniature energy sources. The existence of these organisms shows that biological systems can generate electrical currents without machinery, revealing a surprising connection between life and the movement of charged. Bacteria can form living wires that conduct electricity. Some bacterial communities create long filament-like structures that transport electrons across considerable distances relative to their size. These structures allow entire colonies to share resources and coordinate metabolic reactions that depend on external electron transfer. The filaments behave like conductive pathways, carrying charge from one location to another in environments where oxygen or other electron acceptors are not evenly distributed. The ability to form these biological wires depends on genetic factors, environmental conditions, and the presence of minerals that facilitate electron movement. Scientists study these systems to understand how the microbes organize themselves and how electrons travel along the filaments. The discovery of living conductive structures opens new possibilities for bioengineered materials and devices. It also demonstrates that the natural world has developed its own strategies for moving charge in environments far removed from conventional electrical systems. Scientists are learning to grow bio-batteries for microbial power. Biological systems that generate or transfer electrons can be assembled into devices that produce small but steady electrical currents. These devices rely on communities of microbes, arranged so that their metabolic processes feed electrons into an external circuit. The materials used to house the microbes must allow nutrients to enter, waste to exit, and electrons to move freely toward the electrodes. The electrical output is influenced by temperature, nutrient concentration, and the arrangement of microbial layers. Although the energy generated is modest, the technology offers the possibility of powering sensors, remote monitoring equipment, or environmental devices in places where traditional energy sources are impractical. Ongoing research focuses on improving efficiency, identifying more productive microbial strains, and developing materials that enhance electron transfer. Bio-based electrical systems show that living organisms can participate in energy production in ways that complement mechanical and chemical technologies. They reveal that electricity can emerge from unexpected biological partnerships. Electric sparks can form new molecules out of simple gases. When a strong electrical spark passes through a mixture of gases, it delivers enough energy to break existing molecular bonds and allow new combinations to form. The high temperature and rapid expansion of the spark create a brief environment where atoms and fragments collide with unusual intensity. Under these conditions, molecules that would not normally assemble can emerge within fractions of a moment. Laboratory experiments show that sparks can create complex organic compounds from simple starting materials, such as nitrogen, carbon-containing gases, and water vapor. The process depends on the arrangement of ions, the duration of the discharge, and the surrounding pressure. In nature, similar events occur during lightning strikes, which generate reactive species capable of altering atmospheric chemistry. Scientists study these spark-driven reactions to understand both industrial processes and the potential origins of certain compounds on early Earth. The ability of electrical energy to reshape chemical structures illustrates how closely electricity and molecular transformation are linked. Electricity can sterilize water without chemicals. Applying electrical fields to water can inactivate microorganisms by disrupting their cell membranes or interfering with essential biochemical processes. When a controlled pulse of current passes through a water sample, it alters the electrical environment that surrounds microbial cells. This sudden shift can cause pores to open in their membranes or lead to internal imbalances that the cells cannot repair. The method allows sterilization without adding substances that might change the taste or composition of the water. The effectiveness depends on pulse duration, field strength, and the conductivity of the water. Engineers design systems that deliver precise amounts of energy to ensure that pathogens are removed while preserving the water's natural qualities. This approach is especially useful in situations where chemical treatments are undesirable or where rapid sterilization is needed. It demonstrates how electrical control can influence biological structures directly and provides a clean alternative for producing safe drinking water. Electrical pulses can break apart rocks deep underground. Passing high-energy electrical pulses through rock formations can create fractures by exploiting differences in conductivity and structural weakness within the material. When a strong pulse travels through the rock, it seeks the most conductive pathways, concentrating energy along specific regions. The rapid expansion of vaporized moisture and the sudden thermal stress generate cracks that propagate outward. This technique allows rock to be fragmented without explosives, reducing vibration and minimizing disturbance to surrounding structures. Engineers can adjust pulse frequency, energy, and timing to target particular layers or mineral compositions. The method is useful for mining, geothermal exploration, and tunneling projects where precision is essential. Unlike mechanical drilling, electrical fragmentation can break rock from within, often producing cleaner fractures. This process reveals how electrical energy can interact with solid materials to reshape them in a controlled manner, offering new tools for accessing resources beneath the surface. High voltage currents can sculpt metal with extreme precision. Metal can be shaped or perforated using controlled electrical discharges that remove material from a surface with remarkable accuracy. During this process, a tool electrode is placed close to the metal, and a series of rapid discharges erodes tiny amounts of material. The heat generated in each discharge is localized, allowing intricate patterns or fine details to be created without affecting the surrounding area. The spacing, duration, and strength of the discharges determine the final shape. This approach is particularly valuable for crafting components that require complex internal features or extremely tight tolerances. Because the method does not rely on physical cutting, it can shape hard metals that resist conventional tools. Engineers rely on this electrical technique to produce parts for aerospace systems, medical devices, and precision instruments. The ability to refine metal through carefully controlled electrical interaction highlights the versatility of electricity as a manufacturing tool. Electric arcs can melt steel in moments. An electric arc forms when current leaps across a gap between two conductors, producing intense heat that can exceed the melting point of many metals in industrial furnaces. Controlled arcs are used to melt steel rapidly by concentrating energy directly into the material. The arc's brightness and heat come from the ionized gas that forms between the conductors, allowing current to pass freely. Operators adjust the arc's length, current, and position to maintain efficient melting and ensure uniform temperature throughout the furnace. This method allows scrap metal or raw materials to be transformed into molten steel that can be refined and shaped. The process is favored for its speed and its ability to reach temperatures that would be difficult to achieve through combustion alone. Electric arc technology demonstrates how electrical energy can be harnessed to alter the physical state of metal, supporting industries that depend on continuous production of high-quality alloys. Plasma torches cut through materials using electrified gas. A plasma torch uses a stream of ionized gas to slice through metal, rock, or other solid materials with exceptional accuracy. When gas passes through an electrical arc inside the torch, it becomes energized and forms a narrow column of plasma that carries both heat and momentum. This energized stream transfers thermal energy to the material, melting it along a controlled path. The torch also expels the molten material, creating a clean cut. The quality of the cut depends on gas flow, torch geometry, and current strength. Because the plasma remains concentrated, it can cut quickly, while minimizing heat damage to surrounding areas. The tool is widely used in manufacturing and construction for tasks that require precision and speed. Plasma cutting illustrates how electrical energy can be shaped into a focused instrument capable of altering solid materials with impressive control. Lightning can fuse sand into hollow glass sculptures. When lightning strikes sandy ground, the sudden surge of electrical energy can melt the silica grains along its path. The molten material cools quickly as the heat dissipates, forming long hollow structures of natural glass known as fulgurites. These formations preserve the branching pattern of a lightning channel, creating intricate shapes that extend underground like frozen lightning paths. Their appearance depends on sand composition, moisture content, and the exact properties of the strike. Some fulgurites form smooth interior walls, while others show delicate textures from trapped gas and rapid cooling. These natural glass structures provide clues about the intensity and direction of a lightning event. Collectors and researchers study them to understand the interaction between electrical discharges and geological materials. Fulgurites demonstrate how a brief electrical event can reshape minerals into entirely new structures that capture a moment of atmospheric energy in solid form. Electric charges shape the structure of snowflakes. The delicate patterns found in snow crystals arise partly from the presence of electric charges that influence how water molecules attach. As the crystal grows, as a tiny ice seed forms in a cloud, water vapor molecules bind to its surface in regions where electrical attraction is strongest. The orientation of these charges helps determine whether the crystal develops branching arms, plates, needles, or more complex shapes. Temperature and humidity control the overall pattern, but charge distribution adds another layer of complexity. Slight differences in the electrical environment around a crystal can lead to significant variations in form. Even when crystals grow side by side, as the snowflake falls, collisions with other particles can alter its charge and influence further growth. The role of electricity in crystal formation shows that even seemingly simple natural objects are shaped by subtle interactions among water molecules, temperature gradients, and electric fields. The atmosphere constantly exchanges electrical charge with the ground. The planet's surface and the air above it maintain a continual transfer of charge that forms part of the global electrical circuit. Under fair weather conditions, the ground typically holds a net negative charge while the atmosphere carries a slight positive one. This difference creates a downward electric field that encourages ions to move between air and soil dust. Water droplets and airborne particles help transport charge as they rise and fall. Thunderstorms supply additional charge to the upper atmosphere, reinforcing the separation. The entire system behaves like a planetary scale network of currents that flows quietly under normal conditions. Variations in humidity, cloud cover, and solar activity can influence the strength of the exchange. This natural circulation of charge affects atmospheric chemistry, cloud behavior, and the ease with which static electricity builds up on surfaces. The continuous exchange shows that electrical processes are woven deeply into the fabric of Earth's atmosphere. Raindrops carry tiny electric charges. As they fall, as raindrops form in clouds, they encounter collisions, breakups, and interactions with charged particles that lead to the accumulation of small electrical charges on their surfaces. As they descend, these charges influence how the drops interact with dust, aerosols, and other droplets around them. Charged raindrops can help clean the air by attracting smaller particles that would otherwise remain suspended. Their electrical nature also affect how drops merge or break apart during their fall, influencing rainfall patterns and drop size distribution near the ground. The movement of charged droplets contributes to the overall exchange of charge between the atmosphere and the Earth's surface. Researchers study the electrical properties of raindrops to understand precipitation dynamics and the role of electricity in weather systems. The presence of charge on falling droplets illustrates how electrical processes accompany even the most familiar natural events. Clouds become electrified through collisions of ice particles inside a developing cloud. Countless ice fragments, droplets, and soft hailstones swirl Through rising and sinking air currents, these particles collide with one another repeatedly, and each collision transfers a small amount of electrical charge. Lighter ice crystals tend to acquire positive charge and are carried upward by strong drafts, while heavier pieces that accumulate negative charge settle toward the lower regions. This separation of charge turns the cloud into a natural electrical generator, building strong fields that continue to intensify as collisions proceed. The strength of the field depends on temperature, moisture levels, and the turbulent motion within the cloud. When the charge becomes large enough, the atmosphere can no longer insulate the regions from one another, and a discharge begins. This process forms the foundation for lightning inside storms. The electrification of clouds demonstrates how simple physical interactions among tiny particles can scale into powerful atmospheric events that shape weather around the world. Electric forces help dust grains stick together in space. In the sparse environment of interstellar space, dust grains often collide too gently for gravity alone to bind them together. However, many of these grains carry small electrical charges acquired from ultraviolet radiation, cosmic particles, or interactions with nearby plasma, oppositely charged. Grains attract each other, allowing them to stick upon contact and form larger aggregates. These early clusters become the building blocks for more complex structures that evolve over long periods. The effectiveness of this sticking depends on grain composition, charge magnitude, and the surrounding plasma environment. Small variations in charge can influence whether grains rebound or remain attached. This behavior plays a significant role in the earliest stages of cosmic structure formation, helping matter transition from isolated particles to clusters that can eventually grow through additional collisions. The influence of electrical forces on tiny dust grains reveals how fundamental electricity is in shaping the material found between stars. Planet formation begins with tiny electrically charged grains. The earliest steps toward forming a planet begin when microscopic particles drift within a disk of gas and dust surrounding a young star. These particles often carry electrical charges that influence how they collide and combine. Charged grains can attract one another more strongly than gravity would allow at such small scales, increasing the likelihood that they will stick together during encounters. As clumps grow, their shapes and compositions change, altering how they interact with the surrounding gas over time. Repeated collisions create larger bodies capable of gravitationally gathering additional material. The role of charge is especially important before these clusters become massive enough for gravity to dominate. Electric forces help overcome the natural tendency of grains to bounce apart, enabling the first steps toward building planetesimals. These early processes show that planetary systems emerge not only from gravitational attraction, but also from subtle electrical interactions that help matter coalesce. In the earliest stages of formation, comets spark interactions with the solar wind through electric charge. A comet traveling through the inner solar system releases gas and dust. As sunlight warms its icy surface, the released material becomes ionized when exposed to ultraviolet radiation, creating a cloud of charged particles surrounding the nucleus. As the solar wind flows past, these charged particles interact strongly with the stream of energetic plasma originating from the sun. The encounter generates electric currents and magnetic disturbances that shape the comet's tail and influence its direction. Variations in charge distribution can cause the tail to shift or break into distinct segments. Scientists study these interactions to understand the composition of comets and the nature of the solar wind itself. The way a comet responds to electrical forces reveals information about its environment and the behavior of plasma in space. Comet interactions show that electric charge plays a central role in the appearance and evolution of these ancient objects as they journey around the sun. Saturn's rings pulse with electrical activity from micrometeoroid impacts. The broad ring system surrounding Saturn consists of countless particles of ice and rock that continually collide with one another and with incoming micrometeoroids. When a small impact occurs, it releases charged dust and disrupts the local plasma environment, creating brief bursts of electrical activity. These disturbances propagate through the thin atmosphere surrounding the rings and influence the motion of nearby particles. Spacecraft instruments have detected fluctuations in electric fields correlated with these impacts, revealing dynamic processes unfolding within what appears from a distance to be a serene structure. The behavior of charged particles within the rings provides clues about the composition, density, and age of the material. Electrical interactions also affect how ring particles clump, disperse, or shift over time. Saturn's rings demonstrate that even seemingly delicate features in the solar system are shaped by ongoing electrical processes linked to constant micrometeoroid bombardment. Jupiter's moons trigger gigantic electrical currents through its magnetosphere. Some of Jupiter's moons travel through regions of intense magnetic activity that surround the giant planet. As they move through this environment, their surfaces interact with the magnetic field and the surrounding plasma, creating electrical currents that flow along magnetic pathways. One moon, in particular, ejects ionized material that becomes trapped in Jupiter's magnetic environment, feeding energy into the system. The motion of the moons relative to the magnetic field drives additional currents, producing auroras near the planet's poles and generating radio emissions that can be detected from afar. These interactions depend on moon composition, orbital distance, and the strength of the surrounding field. The electrical connections between Jupiter and its moons form a complex and ever-changing network. Studying these currents reveals how magnetic and electrical forces operate on planetary scales and offers insight into the behavior of extreme plasma environments. Solar flares release oceans of electrified plasma into space. A solar flare begins when magnetic fields near the sun's surface become twisted and unstable. When the trapped energy is suddenly released, it accelerates charged particles to high speeds and heats surrounding plasma to extraordinary temperatures. This eruption sends waves of electrified material outward, carrying energy across the solar system. The intensity and duration of the flare depend on the configuration of the magnetic fields and the amount of energy stored within them. As the ejected material travels through space, it can interact with planetary magnetic fields and influence atmospheric conditions. Spacecraft must be designed to withstand the radiation and electrical disturbances caused by these events. Solar flares reveal the dynamic and often violent behavior of the sun's magnetic environment. Their ability to reshape conditions across vast distances demonstrates how electrical and magnetic forces govern much of the activity in the solar system. The sun's surface boils with endless electric loops of plasma. The visible surface of the sun, known for its roiling texture, contains countless loops of plasma shaped by magnetic fields that rise and fall in continuous motion. These loops form when magnetic lines push through the surface, carrying ionized material with them. As the loops arc outward, they glow brightly and trace the underlying magnetic structure. The plasma within them flows upward, cools, and then descends along the magnetic pathways, creating a cycle that repeats over and over. The size and shape of these structures depend on the strength and arrangement of the magnetic fields that guide them. Observations show loops forming, expanding, twisting, and sometimes erupting when magnetic tension becomes too great. The boiling appearance of the solar surface reflects the constant interplay between heat, motion, and magnetic forces. These plasma loops demonstrate how electricity and magnetism create complex structures within the sun's outer layers. Solar prominences twist into vast electrical ribbons. A solar prominence forms when dense plasma becomes suspended above the sun's surface along magnetic pathways that act like invisible supports. Over time, the prominence can stretch into long ribbons that tower far above the surface. The charged particles within the structure follow the magnetic fields, creating graceful arcs that sometimes persist for days. As the fields shift, the prominence may twist, rise, or collapse, releasing stored energy in dramatic outbursts. The appearance of a prominence depends on the temperature of the plasma, the density of the material, and the arrangement of the magnetic field lines that hold it in place. These Immense structures highlight the delicate balance between gravity pressure and magnetic confinement. Solar prominences show how electrical and magnetic forces sculpt large-scale features on the Sun, producing formations that are both beautiful and scientifically revealing. Spacecraft must protect themselves from charging in space. A spacecraft traveling through space encounters a constant stream of charged particles from the Sun and from distant cosmic sources. As these particles strike the surface, they can deposit charge that accumulates over time. Differences in charge across various parts of the spacecraft can lead to electrical imbalances that interfere with instruments or cause damaging discharges. Engineers design protective coatings, grounding pathways, and shielding materials to manage this accumulation. The behavior of the surrounding plasma, the orientation of the spacecraft, and the type of mission all influence how charging occurs. Sensors monitor electrical conditions so that systems can respond to sudden changes. Proper management of spacecraft charging is essential for maintaining communication, navigation, and scientific operations. This challenge illustrates how deeply electrical processes shape the conditions that spacecraft encounter as they travel through the solar system. Astronauts experience a different kind of static electricity in orbit. The conditions that normally control static charge on Earth behave in unfamiliar ways. A spacecraft contains air that is carefully regulated, yet it is far thinner and more isolated than natural atmosphere at the surface, without a true ground beneath their feet. Astronauts do not have the usual pathways for charge to drain away as they move through the cabin. Clothing rubs against materials that respond differently in this environment, and surfaces retain charge for longer periods. Tools passed between crew members can accumulate small imbalances, and even gentle contact with handrails can create noticeable sparks. Engineers select fabrics, coatings, and interior materials to manage these effects and prevent interference with instruments that depend on stable electrical conditions. Ventilation systems help disperse particles that might carry additional charge, yet the environment remains unlike anything on the ground. The study of static electricity in orbit gives insight into how electrical processes change when gravity, airflow, and grounding contacts are no longer familiar. It reveals that even everyday electrical phenomena must be reconsidered when humans live beyond the surface of Earth. Electricity behaves strangely in a vacuum of space. The region beyond Earth is often described as empty, yet it contains a diffuse mixture of charged particles that create a plasma unlike anything found at the surface. In this sparse environment, electric fields extend over great distances because they are not interrupted by frequent collisions. A spacecraft traveling through this region experiences a constantly changing mix of ions and electrons that can settle on its surface in unpredictable patterns without air to absorb or scatter. Discharge is a small release of charge, can travel along unusual paths or form structures not seen within an atmosphere. Materials that conduct well on Earth may behave differently in a vacuum, developing uneven charge distributions that require special grounding and shielding. The surrounding plasma can also respond to the spacecraft's own electrical systems, creating interactions that influence communication signals or scientific instruments. Understanding these conditions is essential for any mission operating beyond the atmosphere. The vacuum shows that electricity adapts to its environment, revealing forms of behavior shaped by distant sparse particles. In the presence of intense radiation, electric propulsion uses charged particles to push spacecraft forward. Electric propulsion relies on the principle that a spacecraft can move by accelerating charged particles and expelling them behind it. When ions or electrons are guided by electric or magnetic fields, they leave the engine at high speed and impart momentum to the spacecraft in the opposite direction. This method produces gentle thrust, yet it can operate continuously for long periods, gradually building velocity. The system uses much less propellant than chemical engines because the electrical fields do most of the work. The design of these engines requires careful control of ionization, heat management, and power distribution. Engineers must ensure that particles are accelerated along clean paths and that expelled ions do not interfere with the spacecraft's surfaces or instruments. Electric propulsion is especially valuable for long missions where steady performance is more important than rapid bursts of force. The technique shows how controlled electrical processes can become tools for exploration, allowing spacecraft to travel efficiently through regions where combustion is impossible. Ion thrusters produce gentle yet continuous electrical acceleration. An ion thruster operates by creating a stream of charged particles that move through accelerating fields before leaving the engine. To begin this process, neutral atoms are converted into ions inside a chamber, where they can be guided with precision. The ions travel through grids that apply strong electric fields, gaining speed until they exit in a focused beam. Although the force on the spacecraft is small, at any moment the thruster runs steadily and produces a cumulative effect that becomes significant over long journeys. The engine must also emit electrons to balance the departing ions, preventing the spacecraft from collecting excess charge. Power management, temperature control, and propellant flow all influence performance. The appeal of an ion thruster lies in its ability to operate efficiently while consuming minimal fuel. It demonstrates how the careful manipulation of charged particles offers a practical means of propulsion in the quiet vacuum of space. Plasma engines could enable journeys across the solar system. A plasma engine heats a gas until it becomes fully ionized, creating a state of matter where electric and magnetic fields can direct and confine the particles. Once heated, the plasma expands rapidly, and electromagnetic structures guide it through a nozzle that shapes the flow into a coherent stream. The high temperature of the plasma allows it to exit the engine at remarkable speeds, producing thrust stronger than that of many electrically based systems. Engineers design coils and magnetic chambers that control the plasma without allowing it to damage the engine walls. The balance between thrust efficiency and heat management depends on how well these fields confine the plasma and how quickly the system can transfer energy into the particles. This method of propulsion has the potential to shorten travel times to distant planets and outer regions of the solar system. Plasma-based propulsion shows how advanced electrical and magnetic principles can be combined to create engines suited for ambitious exploration. Lightning has been seen on other worlds. Beyond Earth, observations of planets and moons across the solar system reveal that electrical storms occur in many different kinds of atmospheres. On gas giants, towering clouds composed of complex mixtures collide and separate charge in ways that lead to bright flashes visible from space. Rocky worlds with thick envelopes of dust or volcanic gases can also build electric fields capable of producing lightning. Instruments aboard spacecraft record radio pulses, ultraviolet emissions, and brief bursts of illumination that confirm these distant electrical events. Each world has its own conditions that influence how charge accumulates, whether through particle collisions, turbulent winds, or unusual chemical reactions. The discovery of lightning beyond Earth shows that the separation and release of electrical charge is a universal process shaped by the physical behavior of each environment. Studying these events helps scientists understand atmospheric dynamics, cloud chemistry, and energy transfer across diverse planetary systems. Some planets glow with electric auroras never seen on Earth. Auroras arise when charged particles spiral along magnetic fields and collide with gases in a planet's upper atmosphere. On distant worlds, these displays can take forms unfamiliar to observers on Earth because their magnetic fields and atmospheric compositions differ dramatically. Gas giants exhibit auroras that shine brightly in infrared or ultraviolet wavelengths, tracing loops and arcs shaped by immense magnetic structures. Some planets produce auroras far from their poles or generate patterns influenced by interactions with nearby moons. The colors, shapes, and motion of these displays offer clues about the behavior of plasma and the intensity of magnetic fields surrounding each world. Studying these auroras reveals how magnetic environments vary across the solar system and how streams of charged particles interact with planetary atmospheres. The uniqueness of these luminous structures shows that electricity creates visual phenomena that depend strongly on local conditions. The Milky Way is threaded With cosmic electric currents across the Milky Way, charged particles drift along magnetic pathways that extend for immense distances. These pathways channel currents that influence the temperature and motion of interstellar gas. The presence of these currents becomes evident through radio emissions and patterns of polarization that trace the direction of the magnetic fields, shock waves from ancient stellar explosions, rotating clouds of ionized gas, and the motion of charged particles around massive objects all contribute to the formation of these electrical flows. Although the currents are diffuse, their scale allows them to influence how matter collects into clouds that may eventually form new stars. Observations reveal that the galaxy is far from static. It contains a network of plasma and magnetic structures that continually exchange energy. The electrical currents embedded within this network illustrate the deep connection between electricity and the evolving structure of the galaxy. The universe's largest structures hold ancient electric fields, clusters of galaxies, and filaments of gas that span vast cosmic distances, contain faint electric fields that have persisted since the early stages of the universe. These fields developed as matter became ionized and began to move under the influence of gravity and radiation. Although weak compared to fields found near stars or planets, they extend across regions so large that they guide the motion of charged particles over enormous scales. The presence of these fields affects how energy travels through the intergalactic medium and influences the formation of shocks that shape large structures. Observations using radio and X-ray instruments provide indirect evidence for these electrical environments, revealing patterns consistent with long-lasting fields. The existence of such structures shows that electricity plays a role even in regions dominated by gravity, contributing subtle yet meaningful effects to the evolution of cosmic formations. Electricity helps shape the birth of stars as a cloud of gas begins to collapse under gravity. Collisions among particles create regions of ionization where electrical and magnetic forces grow important. These forces guide charged particles along specific pathways, helping the cloud redistribute angular momentum. Without this redistribution, the collapse would proceed differently and might not form the spinning disks that are common around young stars. Electrical currents can arise along magnetic field lines, influencing how material moves. Inward or outward jets of ionized gas may be launched from the forming star, carrying energy away and helping the system maintain balance. The complexity of these interactions reveals that star formation is not solely a gravitational process. Instead, it is shaped by the combined influence of electrical currents, magnetic fields, and flowing plasma. By studying these early stages, researchers learn how electricity contributes to the transformation of diffuse interstellar material into luminous stars. Charged particles spiral through space along magnetic pathways in many regions of the cosmos. Invisible magnetic structures guide the motion of energetic ions and electrons into curved routes that wrap around long arcs of magnetic influence. When one of these tiny travelers encounters such a field, it becomes trapped in a graceful looping pattern that winds forward while circling endlessly around the hidden line of force. This motion is not random. It follows the balance between the particle's energy and the strength of the magnetic environment, creating a helix that can stretch across astonishing distances. These spiraling paths form the backbone of radiation belts, shape auroral displays, and influence the spread of plasma from stars and distant nebula. By studying how these curved motions develop, researchers can map the magnetic topography of space and learn how currents move energy from one region to another. The elegant spiral reveals the dynamic partnership between electrical charge and magnetic structure, a relationship that defines much of the behavior of matter between worlds. Cosmic rays are electrified messengers from distant stars far beyond the orbit of any planet. Powerful events unfold that send streams of energetic particles racing through the galaxy with incredible speed. These travelers cross immense distances, weaving through magnetic regions that bend their trajectories in unpredictable patterns. When they finally reach Earth, they collide with atmospheric molecules and create cascades of secondary particles that scientists can detect From the surface, the information carried in these interactions offers rare insight into environments shaped by collapsing stars, turbulent shock fronts, and extreme magnetic fields. Each arrival contains a small piece of the history of another region of space, altered only by the twists and bends of the long journey. The study of these distant travelers reveals how violent energy can be released into the cosmos and how magnetic landscapes guide that energy across vast reaches. They act as proof that electrical and magnetic forces sculpt the galaxy in ways that can still be measured from the surface of our world. Electricity plays a role in how life first emerged on Earth. Early Earth was a world rich in simple substances, suspended in oceans heated by the planet below, and surrounded by an atmosphere filled with reactive gases. Into this environment came bursts of intense energy from storms, volcanic surfaces, and mineral interfaces, each burst capable of rearranging the atoms within these simple molecules. Those rearrangements occasionally produced more complex structures that could store energy or react in new ways. Experiments show that such electrical events can form compounds that resemble key ingredients of biological chemistry. Although the exact details remain uncertain, it is clear that energetic processes help drive the transformation from a collection of simple substances into systems capable of further evolution. Electrical activity may have influenced how certain molecules interacted with mineral surfaces, how they joined into larger assemblies, and how early chemical cycles formed. This perspective suggests that electrical forces acted not only as sources of energy, but as contributors to the chemical pathways that eventually supported the emergence of life. Electric currents flow through the oceans of Earth. The waters that cover much of the planet carry dissolved ions that respond naturally to electric and magnetic influences as tides rise and fall, as currents shift, and as temperature patterns change. These ions move accordingly, forming subtle threads of electrical flow. Throughout the sea, the planet's magnetic field interacts with these moving waters, creating additional patterns of charge movement that vary from region to region. Sensitive instruments placed in the deep measure these shifts to learn about circulation patterns, underwater volcanic activity, and the distribution of minerals across the seafloor. Many marine species have evolved the ability to sense faint electrical cues in their surroundings, using them to navigate long distances or locate buried prey. The presence of such electrical pathways shows that oceans are not simply passive bodies of water. They form a dynamic environment where motion, salinity, and planetary magnetism come together to create electrical behavior woven quietly into the life and structure of the sea. Lightning helps create compounds essential for life. A powerful electrical discharge passing through the atmosphere delivers energy intense enough to break apart stable molecules and allow new ones to form. When this effect occurs in air rich in nitrogen and oxygen, the reaction produces compounds that can dissolve in raindrops and fall to the surface as valuable nutrients over long periods. This natural process contributes materials that living organisms require, but cannot easily obtain from unaltered atmospheric gases. The heating and rapid cooling of the surrounding air also create additional reactive species that participate in chemical cycles important for ecosystems. Even before life appeared, such electrical activity likely helped enrich surface waters with ingredients that supported early chemistry. By linking atmospheric events to the needs of living systems, these discharges demonstrate how electrical forces influence the availability of essential substances across the planet. The connection between storm activity and biological nourishment is a reminder of the many ways in which electrical energy shapes Earth's environment. Electrical signals allow plants to respond to their environment within plant tissues. Small shifts in charge move along cells whenever the organism experiences touch injury or changes in light and temperature. These shifts behave like quiet pulses that travel through conductive pathways formed by specialized structures inside each cell. When these pulses reach distant regions of the plant, they trigger adjustments, such as closing leaf pores, releasing protective chemicals, or altering growth patterns. The speed and intensity of these signals depend on water content, internal pressure and the arrangement of vascular tissues. Some species create widespread, coordinated responses when a single leaf is disturbed, showing that information can spread rapidly through electrical means without a nervous system. Researchers observe these pulses to understand how plants perceive their surroundings and make decisions that affect survival. The presence of electrical communication within such organisms highlights a deeper truth. Many forms of life rely on charge-based signaling to organize their behavior, even when their structures differ greatly from those of animals. Pain and touch are carried through the nervous system as electric patterns. A sensation begins when specialized cells at the body's surface convert pressure, heat, or injury into rapid changes in voltage. These changes travel along slender fibers in the form of moving waves that shift the electrical balance from one segment of the fiber to the next. As the waves progress, they reach connections where the signal is passed to other cells that continue carrying it toward the spinal cord and eventually the brain. The pattern created by these waves determines how the brain interprets the sensation. Gentle contact produces one pattern, sharp discomfort another. The system can adjust its sensitivity depending on context, allowing heightened awareness during injury or reduced perception during rest. The structure of each fiber, the composition of its insulating layers, and the arrangement of its connections all influence how quickly and accurately the signal travels. The conversion of physical events into electrical patterns shows how the nervous system transforms the external world into meaningful internal experience. Muscles move because electrical pulses trigger tiny molecular motors. Movement begins when a nerve fiber delivers a brief electrical change to a muscle cell, causing charged particles to flow across its surface. This shift sets off an internal cascade that releases signals stored within the cell. Those signals allow two types of protein structures to interact in a coordinated manner, pulling against one another and shortening the cell. When many cells shorten together, the entire muscle changes length and produces motion. The force generated depends on how many fibers receive the electrical pulse and how often the pulses arrive. The system can sustain fine control for delicate tasks or generate powerful contraction for rapid movement. The reliability of this mechanism comes from the tight relationship between electrical cues and the molecular structures that respond to them. This connection allows organisms to translate simple electrical instructions into complex physical actions that support walking, grasping, breathing, and countless other behaviors. The heart beats because of a self-generating electrical rhythm. A small region within the heart contains cells that naturally cycle through changes in voltage, creating pulses that spread outward through surrounding tissue. These pulses coordinate the contraction of chambers that move blood through the body. As the electrical wave travels, it encounters regions designed to slow its progress, ensuring that one chamber empties before the next begins to contract. The frequency of the rhythm changes depending on signals from the nervous system, hormones, and internal conditions such as oxygen levels. If the sequence becomes irregular, circulation can be compromised, which is why medical devices often assist in restoring stable electrical patterns. The heart's reliance on a self-generated rhythm reveals how electrical processes can govern major physiological functions. This rhythm persists throughout life, adjusting continuously to support the needs of the organism. Sleep cycles are guided by shifting patterns of brain electricity. During sleep, different groups of neurons engage in rhythmic electrical activity that changes as the night progresses. Slow waves spread across broad regions during deep rest, while bursts of coordinated pulses appear during stages associated with memory processing. Rapid oscillations emerge during periods when dreams are most vivid. These shifting patterns arise from networks reorganizing their communication pathways, strengthening some connections and quieting others. External cues, such as daylight temperature and behavioral routine, influence when these cycles begin by affecting internal clocks that regulate electrical timing. Monitoring these rhythms provides insight into the function of sleep and its role in maintaining cognition, emotional health, and physical restoration. The constant reconfiguration of electrical Activity shows that sleep is not a passive state, but an organized process guided by precise electrical signaling. Creativity emerges from complex electrical patterns in the mind. Original ideas arise when different regions of the brain communicate through shifting rhythms of electrical activity that allow concepts to blend in novel ways. These rhythms guide how information flows between networks that normally handle separate tasks, such as memory, imagery, language, and emotion. When these networks synchronize in unusual combinations, the mind gains access to associations that are not easily reached during more routine states. The degree of flexibility in these electrical interactions shapes how new solutions appear and how breakthrough moments emerge. Factors such as rest, curiosity, and exposure to new experiences can encourage patterns that support inventive thought. Researchers observing these signals find that creative insight is not a single event, but a dynamic process in which electrical coordination evolves over time. This continuous reorganization allows the mind to explore possibilities beyond established pathways. The presence of such adaptable electrical landscapes shows that creativity depends on the brain's ability to reorganize and reconnect its own internal currents. Emotion is linked to distinct rhythms of electrical activity. Different emotional states correspond to identifiable patterns of electrical signals moving through various regions of the brain. These patterns guide how attention shifts, how memories feel, and how the body prepares to respond. Some states encourage slower, more expansive rhythms, while others generate rapid bursts of activity that heighten awareness or sharpen focus. These electrical changes influence breathing, heart rate, and hormone release, showing that emotion is not solely a mental experience, but a coordinated physiological response. Subtle variations in these rhythms can alter how a person perceives surroundings or interprets social cues. Scientists studying these electrical signals find that they vary widely among individuals, shaped by experience, temperament, and environment. The ability of emotion to reshape electrical behavior demonstrates the deep link between brain activity and feeling. This connection helps explain why emotional states can shift quickly and why they affect both thought and physical well-being. Memory forms when electrical pathways strengthen connections between cells. The formation of memory depends on repeated patterns of electrical activity that gradually reinforce the connections linking one neuron to another. When a particular experience is recalled, similar electrical patterns emerge and strengthen the pathways involved. This process relies on changes within the cells themselves, which adjust their sensitivity to incoming signals. Neighboring cells also reorganize their communication channels, allowing information to move more efficiently along routes that have been used frequently. Over time, these strengthened pathways create a stable representation that can be accessed even long after the original event. The durability of memory depends on how often these electrical patterns reappear and how strongly the involved cells adapt. The interplay between structure and activity allows the brain to store vast amounts of information without relying on a single location. Memory emerges from coordinated electrical changes that transform fleeting experience into lasting knowledge. Learning changes the electrical architecture of the brain. Learning involves a continuous reshaping of the brain's electrical organization as new skills, ideas, and associations develop. Whenever new information is encountered, networks of neurons adjust their responsiveness, allowing electrical signals to travel along different routes. Some regions become more active while others quiet down, depending on the demands of the task. This reorganization enables the system to operate more efficiently as knowledge accumulates. Practice strengthens the pathways that support accurate performance, while unused routes gradually fade. The brain remains flexible throughout life, adapting its electrical landscape to changing environments and goals. This adaptability allows complex behaviors to become automatic or intuitive through repetition. Observing these shifts reveals that learning is not merely the accumulation of facts, but a transformation of the electrical patterns that shape perception, movement, and understanding. The living architecture of the brain evolves with each new experience. Electricity allows remote communication across vast distances. Long-distance communication relies on the ability to convert information into electrical signals that can travel through conductive pathways or be transformed into waves that move through air and space devices at the sending end, encode speech images or data into patterns of current that change rapidly over time. These patterns journey through cables or become electromagnetic waves that extend far beyond the limits of wired infrastructure. Receivers then convert the signal back into a recognizable form. The clarity of this process depends on the quality of the electrical encoding, the stability of the transmitting medium, and the precision of the receiving components. The entire system operates through the predictable behavior of electrical signals flowing across great distances without distortion. When properly guided, this principle supports global communication networks, allowing information to move between continents with remarkable speed. The interconnected world depends on the reliability of these electrical pathways. The global power grid is one of humanity's largest living systems. The network that delivers electricity to homes, cities, and industries functions as a vast interconnected organism with countless components reacting to continual changes in supply and demand. Power plants generate the flow, while substations guide and transform it. Transmission lines act as long arteries, carrying energy across continents. Sensors monitor the health of the system, and automated controls adjust flows to maintain balance. This coordination must occur in real time because even small variations in usage or generation ripple through the entire network. Unexpected weather, equipment failure, or rapid shifts in consumption require immediate adaptation. Engineers design the grid to anticipate these fluctuations by incorporating reserve capacity and multiple routing options. The complexity of this structure allows electricity to reach distant regions while supporting the stability of densely populated areas. The grid's responsiveness and scale make it one of the most intricate systems ever created. Electricity can travel through the ground faster than through wires. Certain conditions allow electrical energy to move through the Earth's surface layers more rapidly than through metal conductors. Moist soil, mineral-rich rock, and groundwater can form pathways that carry electromagnetic pulses over long distances with remarkable speed. These pulses do not behave like ordinary current inside a wire. Instead, they propagate as waves that spread outward along the Earth's surface, influenced by soil composition, moisture levels, and nearby geological structures. Utilities use controlled versions of these waves to detect faults in buried infrastructure or to locate breaks in long transmission lines. Natural events, such as lightning, also send pulses racing through the ground, distributing energy far from the original strike points. Studying these phenomena helps scientists understand how the planet responds to electrical disturbances and how information can travel through complex materials. Some storms create mysterious invisible flashes called sprites high above. Intense thunderclouds, faint electrical events, occasionally unfold in the upper atmosphere, creating patterns known as sprites. These events are triggered by strong discharges occurring far below, yet their appearance forms in a region where air behaves differently than it does at lower altitudes. The resulting structures can resemble branching trees, expanding glows, or rapidly shifting patches of light. Their colors and shapes depend on the composition of the thin air and the strength of the fields involved. Although visible from aircraft or sensitive cameras, they're often missed from the ground because they occur so high above storms and last for only a brief moment. Observing these elusive events helps researchers understand how electrical activity moves between atmospheric layers. Sprites reveal that storms influence far more than the weather directly beneath them. St. Elmo's fire is a glow formed by air becoming electrically charged during certain atmospheric conditions. Strong electric fields can cause molecules near sharp edges or pointed surfaces to become ionized, producing a distinct glow known as St. Elmo's fire. This phenomenon often appears on ship masts, aircraft wings, or tall structures. When storms are nearby, the glow forms because the electric field around these objects becomes intense enough to energize surrounding air, creating a soft emission of light. The color and brightness depend on humidity, air pressure, and the specific molecules involved. Although visually Striking the event does not represent a full lightning discharge, but rather a gentle release of electrical energy. Sailors and pilots have long observed this glow, using it as a sign that atmospheric charge is building. Studying this effect provides insight into how electric fields behave around surfaces and how the boundary between charged air and solid materials can produce luminous displays. The future of energy may rely on new ways to control electric charge. Research into advanced materials, storage systems, and generation methods suggests that future energy technologies will depend heavily on precise control over the movement and arrangement of electrical charge. Novel substances can guide electrons through complex channels, convert light or heat into current with improved efficiency, or store charge in structures far different from traditional batteries. Engineers explore methods that manipulate charge at very small scales, creating devices that respond instantly to changes in demand or environmental conditions. Large systems may also shift toward distributed networks that balance supply and usage in real time. These innovations aim to make power production more resilient, adaptable, and sustainable. The direction of energy research indicates that understanding how charge moves through different environments will shape the next generation of global infrastructure. Electricity's potential continues to expand as new techniques reveal ways to harness and direct charge with increasing precision. As we reach the end of this quiet journey into the strange and shining world of electricity, allow yourself to soften, let your breath ease, let your thoughts drift into the gentle space that opens when curiosity finally begins to rest. All the glowing currents and hidden patterns we explored tonight can settle now into a calm hum at the edge of awareness, a reminder that the universe is always alive with motion, even when you close your eyes. If you enjoyed this peaceful exploration, I invite you to like, subscribe, or share a thought below. It helps others find their way here to one sleepy soul at a time. You are welcome to return whenever you wish for another slow wander through the quiet wonders of science. But for now, allow the day to fade away, let your mind grow still, and allow the gentle darkness to gather around you. Good night.